Welcome everybody to our new session. The session sponsored by IonQ. We have the pleasure to have on stage Sonika Johri. We welcome you, Sonika. Let me introduce and tell the audience about you. Sonika Johri is a senior quantum applications researcher at IonQ, a company commercializing trapped ion quantum computers. Her research centers around translating the rapidly expanding capabilities of quantum hardware into measurable advantages for end users of quantum computing. She leads IonQ's effort in developing applications for current and near future generation of quantum computers. She has co-authored several publications involving cutting-edge quantum algorithms demonstrations in the areas of generative and discriminative machine learning, condensed matter physics, quantum chemistry, and optimization across a variety of quantum hardware platforms. Her work emphasized the co-design of quantum algorithms, software, control, and hardware in order to come up with practical and scalable solutions that are aimed at making quantum technologies highly impactful as soon as possible. Prior to IonQ, she worked as a quantum algorithms researcher at Intel Corporation. He has a PhD in theoretical condensed matter physics from Princeton University. So, Sonika, welcome to the stage of Quantum-Latino. The floor is yours.
Thank you, Rafael. Just want to confirm, do I have half an hour or?
Yes. So I will hide myself and will be back 5 minutes before to remind you, okay?
Great. Thank you so much.
Bye-bye. You will see at the right question and answers. I will follow it, and if you want to look at there, but I will look and we'll be back with that, okay?
Okay, great. So can people see my screen? Can someone tell me if they're seeing it?
Yes.
Awesome. Yes. Thank you.
Now we can see the PowerPoint. Now it's full screen.
Awesome.
Okay.
Thank you so much. So hello, everyone. Thanks for coming to attend my talk. My name is Sonika Johri, and I'm a senior applications researcher at IonQ. And I'm going to talk to you about running algorithms on trapped ion quantum computers. So a little bit of introduction to the trapped ion quantum systems at IonQ. The underlying qubit in our technology are ionized atoms, which are held in place by lasers, right? So effectively, you can, if you want to draw it out schematically, you would have all of these ions sitting in a line. And then the quantum computation is done by a series of operations called gates, which manipulates the qubit states. And these gates are implemented by an array of laser beams. If you consider the circuit model of computation, which is currently the most popular programming paradigm for quantum computers, it can be represented by this schematic on the top right where I'm pointing to with my mouse. So over here on the x-axis, you have time, and on the y-axis, you have the different qubits which are initialized in the state 0. So then when you begin your computation, the rectangles over here denote gates, and then corresponding to the gates, to the qubits on which those gates are acting, laser beams are going to hit the corresponding ions. That's how the quantum operation is going to be implemented. And then in the end, when you want to read out the state of the qubits, that is also done by laser beams. So now, since these lasers can hit any individual atom or even all of them at the same time, so this in turn implies that the system is extremely reconfigurable, as well as the connectivity is very high, right? And the connectivity is high because any two atoms can be entangled with each other because they interact via the Coulomb interaction, which is long range. Right? So for any of you who are who have ever programmed, who have ever written quantum programs and tried to execute them on one of the near-term quantum computers, you will immediately recognize the benefits of a high connectivity hardware quantum hardware platform, right? Because that just means that you can you have to use much less swap gates, and this directly translates to much superior algorithmic performance. Now, IonQ also has a vision for scaling up its quantum computers, and this is via the use of photonic interconnects, right? So if you have different ion traps, each containing a certain number of ions, you can couple different modules using these photonic interconnects, and thus effectively allow for almost indefinite scaling. And so this is currently pretty much the only realistic modular quantum computer architecture we know about. And here is a video that one of my colleagues took of our ions sitting in the ion trap. And I think there are, I'm not sure, maybe about 22 or 30 ions in this picture, right? And they're held in place by laser beams. And you might be wondering why we are working with atoms and what are the advantages of picking this hardware versus others. And it essentially comes down to atoms are nature's qubit, right? Now, since each atom is given by nature to be exactly the same as every other atom in nature, all our qubits are completely identical to all our qubits are completely identical. And they're also naturally quantum objects. So unlike solid-state qubits, where the qubits are subject to a lot of fabrication errors and very sensitive to defects in the underlying substrate, our atoms are much more our qubits are much more robust. They're also very well isolated. So since they are suspended basically in space, held together by laser beams, they're extremely well isolated from environmental influences. And this is also unlike other fabricated solid-state qubits that are bonded to a substrate, so they're extremely sensitive to whatever is going on in that substrate. And also, no novel fabrication techniques are used in our technology, and a commercial silicon fab works great. The current systems on our cloud have 11 qubits, and there are a lot of perks when running on our systems. So first of all, as I mentioned, we have all-to-all connectivity, so you can run gates between any pair of qubits. And also the fidelities are extremely consistent across the entire chain of ions. Again, different from many of the hardware technology, that's pretty different from many of the solid-state qubit technologies. Another really attractive feature of our platform is that the user or the programmer does not have to know anything about the physics of the trapped ions, right? You can write your program at the logical level, and we will compile and optimize those high-level quantum logic gates for you. Right. So really at IonQ, we have this vision that our systems are not physics experiments, they're actually computers, right? And you should be able to increasingly use them the way you would use a classical computer, right? And you don't have to go and do a PhD in physics or really, read a lot of research papers on ion physics to be able to use our systems. Then thirdly, our systems are also automatically calibrated, and they run 24/7, so you can submit a job over the cloud and it will be executed for you. You do not need to know anything about how it is calibrated. You don't need to worry about calibrating it yourself to get slightly better performance. We will do all of that for you, and you can expect that your results will be pretty consistent from run to run over time. So really moving towards the vision of having having it be like any other computing resource you might use over the cloud. So in this talk, I really want to focus on applications of our trapped ion quantum computer. So we've recently had a couple of really interesting publications in doing machine learning on our computers. right? And I'm going to talk in detail about this one on the bottom right here, which was doing nearest centroid classification on our systems. And other than machine learning, there's also a lot of work on many-body, what I would call quantum many-body systems, which is like condensed matter physics or quantum chemistry. And if you go to our website, you'll find several papers that are on those topics as well. So let's come to the meat of my talk, which is basically doing nearest centroid classification on a quantum computer. And this falls in the field of quantum machine learning, which recently has gotten a lot of hype. And the reason for this is obvious, because machine learning has such a wide range of applications that it is an attractive area for quantum computers. And if you can show that a particular machine learning algorithm has an advantage on quantum computers, there will be many takers for it, basically. However, the caveat is that the quantum machine learning algorithms that we know have provable speed up, they seem to only work on long-term fault-tolerant machines, right? Because they have very heavy resource requirements. So we cannot really envision them working on near-term machines. And on the other hand, there are several near-term algorithms which are usually based on variational circuits, but they somehow rarely have proofs. And since we do not have large enough quantum computers yet, they cannot be tested at scale. And so in this work, what we're trying to do is bring quantum machine learning a little bit closer to reality. The particular application we will look at is classification, right? And so now all of you are probably familiar with classification. So for example, you can, one cute application of classification may be differentiating between pictures of cats and dogs, right? A more serious application could be identifying images of tumors from scans of the brain, right? In this particular project, we worked with two data sets. One was the iris data set, which consists of 3 classes, each corresponding to a different variety of the iris flower. And each data point in this data set has 4 dimensions, each corresponding to the width and the length of the sepals and the petals of the iris flower. And then the second real data set that we worked was this MNIST data set, which consists of handwritten images of digits, right? And it's a pretty it's used as a benchmark for several machine learning algorithms. So we also decided to use that. So the first thing to do when you want to do a machine learning task is, of course, to pick an algorithm. And so in this case, we use a very simple algorithm. It's called the nearest centroid classifier. And the way it works is that first you find the centroids of each class of training data, right? So let's say you have a training data set. You have a data set with 3 classes, right? Let's say shown by the blue, green, and red circles over here. Right, and then for each class, you pick you calculate the centroid of you calculate the centroid of that class, right? So over here, it's these shaded circles over here, right? And now, when you are given a new data point, let's say this point in white over here, the way to classify the data point is to compute the distance to each of the centroids, right? And then you assign that point to the class for which the distance to the centroid is the minimum, right? So now to run this algorithm on a quantum computer, what we do is the subroutine of computing the distance to the centroids, we do it on the quantum computer, right? And I also want to mention that even though this algorithm is quite simple, the nearest centroid classifier, it is also a subroutine of the k-means algorithm, let's say, and that is, it's a very commonly used algorithm in unsupervised machine learning. So once we have the algorithm in mind, we design the quantum circuit, and basically what we want to do with the quantum circuit is estimate the distance between 2 data points and x and y. So let's say x and y are 2 vectors of real numbers, and we want to find the distance between them. So our colleagues at QCWeb, in collaboration with whom this project was done, they built a circuit that does exactly that. And so this circuit, you can see it consists of, if you draw a line down the middle, it almost looks like a mirror image. So the first half of the circuit is used to load the data into the quantum computer corresponding to the data at point X. And then the second half of the circuit executes gates that correspond to the adjoint of the circuit that would be used to load the data point Y into the quantum computer. And then if you measure the first qubit over here, you're essentially going to get the dot product between X and Y, which can in turn be used to calculate the distance between X and Y. This particular circuit has some nice properties in that it is shallow. So it is only, so if you have 8 qubits, it is only log of 8 in depth, 2 times log of 8 in depth. So n qubits and 2 to the log n depth. This circuit can also be generalized to use any other data loader with the same basic structure of like having the loader X plus the adjoint of the loader Y. And it can be combined with other quantum techniques like amplitude estimation to get even more of a speed up. So in this particular project, when we wanted to transfer the real data into the quantum computer, we used a Unary encoding in which the number of qubits is equal to the dimension of the data point, right? So it's quite a sparse encoding, but it turns out to be very useful, as I'll show later. The output state on the ideal quantum computer would produce a state of this form, right? So it's a unary encoding, which means that in the encoding subspace, only one of the qubits is in the 1 state and all of the other qubits is in the 0 state, right? And so then you can have a superposition of these, right? So if you wanted to encode a data point which corresponds to the vector with elements A1, A2, A3, this is how you would store them. And then your algorithm, it requires the estimation of A1 square at the end. And so this is what the state would look like on an ideal quantum computer. However, when you go to a real quantum computer, right, you go to a real quantum computer that is available on the cloud today, since that quantum computer has noise, there will be finite probability outside of this unary encoding subspace as well, right? And so here, an example of this is shown on the left, right? So if you have 8 qubits, instead of something that looks like, an ideal probability distribution that looks like the one on the right, you have something that looks like the one on the left. And so one thing you could do is you could just calculate A1 square from this histogram directly. The second thing you can do is, apply some error mitigation. And the technique we used here was to post-process this histogram on the left to discard erroneous states. And so basically, you're discarding some of the counts that are corresponding to states that are outside of the unary encoding subspace. And then once you do that, you have a probability distribution with probabilities that don't sum to 1 anymore. And so you renormalize that so that they do sum to 1, and then you get something that looks like the one on the right. And this, as you'll see, will give us much better answer. So then we ran the algorithm on the IonQ machines. We tested it on the R11 qubit system that is on the cloud. The native gates used for this experiment were single qubit rotations and maximally entangling Volmer-Sorensen gates. The average fidelity of the 2 qubit gates that is available to the average user of the cloud is more than 96%, and we tested 4 and 8 qubit versions of the circuit. And the number of 2 qubit gates for the 4 qubit circuit was 12, and for the 8 qubit circuit was 30. So now let's look at some of the results. And now over here, I should apologize because the dark blue over here corresponds to the raw data, and then actually this should be orange in color, but that's the results after post-processing. So the right one in orange is results after post-processing, and the blue is the results before post-processing. And over here, I'm showing the classification error percentage, right, for different data sets. And NQ over here is the number of qubits. NC is the number of classes in that data set, and NS is the number of shots that we took for each circuit. Now we can see that for the simplest data set we ran, where we had a 4-qubit circuit and 2 classes, there were no errors. Even without any post-processing, there was no errors. Now when we increased the number of classes from 2 to 4, there was some small amount of error. And when we went from 4 qubits to 8 qubits, suddenly the error shot up quite a bit. But however, once we post-processed that, there were again no errors, right? And then when we went from 8 keeping the number of qubits as 8, we went from 2 classes to 4 classes. The error increased further increased before post-processing, and after post-processing, again, you can see that the error came down quite a bit. Next, let's look at the results on the IRIS data set, which is the real data set. So this required 4 qubits to run, right? Again, we ran it. For different number of shots, and here you can see the effect of increasing the number of shots. The dashed line over here is the error of the equivalent classical classifier. And again, here you can see that after post-processing, the error reduces quite a bit. And then again, if you increase the number of shots, the error further reduces. You do see, however, that increasing the number of shots from 500 to 1,000 does not further reduce the error, just showing that, if you have some noise in your quantum computer, right, it's just increasing the number of shots more and more will not necessarily get you a lower error if you already kind of at the threshold of the maximum information you can get from the system. Over here on the right, I show you the results before and after error mitigation visually. So this is a 4-dimensional data set, but I've used principal component analysis to project it down to 3 dimensions. And you see so over here, the color of the circles is the class assigned by the human classification, and then the color of the stars is the class assigned by the quantum computer. And you can see that before error mitigation, there are points that are in between the 2 classes, right, that are mislabeled by the quantum computer, right? However, the points that are that are clearly within each class are classified correctly. And once you apply the error mitigation, these points move over into the correct class, right? So it's kind of showing you the effect of the noise on a quantum machine learning algorithm, that the points that are kind of in between classes can be misclassified, and also by applying error mitigation, even those points can be moved over into the right class quite often. Now let's look at the results for this MNIST data set on 8 qubits. Here, the diamonds are showing the results of the classical classifier, right? And again, we looked at different subsets of the MNIST data set. So we looked at just the digits 0 and 1, and classification between digits 2 and 7, and then classification of these 4 digits 0, 1, 2, 3, and then also classification of all 10 digits. And you can see that in each of the subsets of the data that we ran the experiment for, after error mitigation, the error of the quantum classifier is almost the same as the error of the classical classifier. And again, here is just the confusion matrices for the MNIST data set between the target class and the output class, and you can compare the classical and the quantum, and you can see it is pretty close to each other. And then finally, in this era of NIST computers, people talk about error mitigation quite a bit, but what I find is often they do not talk about how this error mitigation is going to scale as the problem size increases. So we thought it was important to go in and do this analysis. And so we see that, so we did this analysis of how the noise is affecting the accuracy of our algorithm, and how the error mitigation technique is going to scale as the system size increases. So we recognize that there are 2 types of error in our experiment. One is an error that when you have the ideal density matrix, it just redistributes the weight within the ideal density matrix. So this is something that I would say you could call some kind of coherent error, right? And what we find is that since we are only measuring we are only measuring, as the output of our algorithm, we are only measuring the probability of one of the qubits. And the number of gates acting on that qubit is log n. This error will grow very slowly. The second kind of error that we looked at is this depolarizing error, which basically redistributes the weight from the ideal density matrix to a completely mixed state. Then we went in and did some analysis and found out that actually the error mitigation technique that we apply will get more effective at removing this error as the number of qubits increases, if the fidelity is over a threshold, which is about 86%. And as I mentioned earlier, the fidelity of our 2-qubit gates is at least 96%. And therefore, our post-selection technique is actually very powerful. So I will conclude with that. Basically, we ran the quantum nearest centroid algorithm successfully on our cloud quantum computers. And used it to classify several real-world data sets. And one of those data sets had up to 10 classes, and we got remarkable accuracy, matching the classical classifier accuracy with that. And what enabled us to do this was the choice of a sparse encoding, which in turn allowed for very effective error mitigation opportunities. And you can find the paper currently on arXiv, and it should soon be in a journal as well. Thank you.
Thank you, Sonika. Thank you very much. Great presentation. Great to have brought to us practical implementations of applications of quantum algorithms. And it is good, I think, for the audience to have also some idea of how big the problems can be now. And maybe you can tell us something about the future. How is this growing? Does you or does IonQ expect this to grow?
Yeah, so our newest generation system has 32 qubits, right? And, much higher gate fidelities, right? So, the current has like average 96, and I think the target for the new one is 99.9%, right? And so you can imagine that the current algorithms that I described, right, they're going to be legacy almost, right? The new algorithm, that kind of algorithms that we can do on the new system will be just several magnitudes more complex, and we'll be getting a lot of new exciting results and learning how to program these new generation of quantum computers. And you can look I think on our website you can find like our technical roadmap, and you can see that it is pretty ambitious, and I'm pretty confident that we're going to execute on that. And yeah, it's a really exciting time to be in the field as a quantum algorithms developer, where you can actually go in and start testing all these ideas. And yeah, it's a very fruitful and productive time to be in the field.
Indeed. So we have a couple of questions from the audience. Thomas Clark asks you, thank you for your talk. Perfect level of technical detail. Out of curiosity, what are your thoughts on the room temp ion traps developed by Universal Quantum?
So probably I don't want to comment on any other company's technology, but it is true that I think trapped ion quantum computers, they don't require you don't require like a big dilution refrigerator. And you don't require liquid helium or anything like that, right? So it is a technology that works close to room temperature, and that in turn makes it suitable for a variety of things that other technologies cannot, right? You can think about deploying it in a lot of different situations, and like kind of miniaturizing it, and I don't know, putting it on a plane, putting it in space. I don't know. There's just a lot of exciting things that are available when you can work with things that are close to room temperature.
Excellent. And we have a final question from Michelle. Very interesting, Sonika. I enjoy it a lot. Could you mention some downsides of ion technology? Also, what would you say are the best kinds of problems to solve with an ion computer, and which not so much? Thank you very much and congratulations.
Yeah. So it's hard for me to think of any downside. So personally, as a researcher, I've worked with several different kinds of qubit hardware, right? So I've worked with like a couple of different superconducting qubit platforms. I've worked with trapped ions. I've also, done some research with like, spin qubits. And for me, like this is hands down the best one, right? In terms of the accuracy of the results that you get, it's not even close to being that on any other platform, right? Yeah, it's hard for me to think of any downsides compared to other platforms. Compared to classical computers, right, it is still slow, right? But there are paths to kind of increasing the gate speed quite a bit, right? And I'm pretty confident that we'll get there. Yeah. In terms of what problems that is it really suitable for, I think any problem that requires high connectivity and high fidelity, gate fidelity, is really runs really well on trapped ions. And now that's almost every problem, right? Like every quantum algorithm at scale will benefit from having a highly connected system, and it will also benefit from having high gate fidelity. So I think almost any algorithm at scale will likely run better on trapped ions.
Here, Ivan comments portability and scalability. So, Sonika, thank you very much for your presentation. Great presentation. We will study deeply the papers you presented. And let me make a couple of announcements for the audience in English and then in Spanish. So we have now 25 minutes for break for lunch, and 25 minutes from now we will start the next session. So come back and you can use this time to visit the booths and the networking area. So we'll switch to Spanish. Ahora en 25 minutos y media nos encontramos nuevamente. Ahora hacemos una pausa para almuerzo y para relajarse, y podemos aprovechar para visitar los booths y el networking, el área de networking. Bueno, así que en 24 minutos nos encontramos. So, Sonika, thank you very much once again for your presentation. I will end the session.
Thank you.
See
Bye.
you soon. Bye-bye.